Okay, so in the previous video, I made the point, discrete time, LTI systems, exponentials in, exponentials out, complex exponentials in, complex exponentials out, sinusoids and sines and cosines in, sines and cosines out, and the frequency is respected. It doesn't change. All right, so let's go on to slides 12 and 13. So he likes this business about vector diagrams. Let's see, where are we? All right. So here's a impulse, Laplace transform of impulse response, and he wants to see what this is going to do to a signal. So if you take one of these terms, like z0 minus q0, this first term in the numerator, it's going to have an amplitude and a phase, and you can represent it as a vector in complex space. Right. So he's trying to show the effect of this coefficient on your signal. And this is the math part, that the magnitude is going to be the product of the magnitudes, well, product and quotient. And the phase is add. Remember, that's how you deal with complex numbers in polar form. The modulus is add, the modulus is multiply, and the phase is add. Now, in my preliminary notes, I criticized slide 14, but now that I look at what he's doing, it's actually quite good. So I'm going to cross this out. Okay, here. Okay. All right, so it is true that the input e to the j omega n produces the output like this. And then he says, similarly, the input with a minus, right? The input, let me call this x prime or something, and this would be with a minus. It produces the output with a minus. Okay. Now, since we're interested in real signals, this is what I mentioned before, that to get a real signal, you would take x of n plus x prime of n, because then that will give you the real part of x. So that's what he says here, that the the output is the sum of the outputs, and then the key point here is that the h of the complex conjugate is the complex conjugate of h, and that's not immediately clear. That's only clear because these h of n's are real. If the h of n's were not real, then that would not be true. Right. But this is, like I said before, do the calculation in complex space and then take the real part at the end, and you'll get the correct answer. Right. So when the input of x is the real part of e to the j omega 0 n, then the output is going to be the real part of h of e to the j omega times e to the j omega n. Right? And so you remember, the real part of a complex number in complex polar form is equal to the magnitude times the cosine of the phase. And the phase is given by the original phase, which is omega 0 n, plus the phase added by the impulse response. Okay, so the magnitude and phase of a response of a system to an eternal cosine signal is the magnitude of the phase evaluated on the unit circle. So my comment here, he's breaking it out into polar form. The system will change the amplitude of a sinusoidal input signal by the amplitude of h, and it will change the phase by the phase of h. Okay, and he's emphasizing that when we look at discrete time signals, we're interested in the values of h of z when z is on the unit circle. So important to look at the unit circle here. When we were doing continuous time, we were looking at the imaginary axis, right? We replaced s with j omega. But here we're replacing z with e to the j omega n, which is a complex number of unit unit magnitude. Now the next several slides talk about these vector diagrams, and it's not critical to understand what's going on here. It gives some intuition. So for instance, if you want to see what this impulse response is going to do to your signal, you're trying to see what the magnitude and the phase of this number is. So notice the numerator is z minus q1. Here q1 is the 0, which is represented by this circle. The denominator is z minus p1, and p1 is the pole, which is represented by the x. Right? So z minus q1 is going to be a vector from the point z to the 0, and z minus p1 is going to be a vector from the x to your point. So here we're looking at the case where z is equal to 1. Remember, we're looking at the unit circle. So z equals 1 is this point. So that corresponds to the omega is equal to 0, right? Minus pi to pi. He's plotting the omega here. He's plotting as a function of omega. The other thing is that the numerator and denominator are both real. So positive real has complex phase of 0. So that's where this point comes. Right? And he's going to run the point around the circle and see how these vectors determine the phase and the amplitude. Right? So if I'm here, I've got my two vectors. This is the numerator vector, this one here. And this is the denominator vector, this one here. Now you can see that these two vectors are of more equal size. In the first picture, the vector to the 0 was quite a bit longer than the vector to the pole. Right? Here they're of more equal size. So if you take the ratio, it's going to be smaller. So that's why it goes down. Now what about the phase? Well, what you need to do is take the phase of z minus qi and subtract the phase of z minus pi. Now what's the phase of z minus qi? Well, that's this angle from, I don't know if I can show this clearly, but see this vector here, from the 0 to the point. The phase of the numerator is going to be that angle. Right? It looks something like 60 degrees. All right? The phase of the denominator is the angle made by this vector here with the x-axis. That's a steeper angle. Right? This is 60 degrees, this might be 70 degrees. It's closer to 90 degrees. Right? So I take the difference of these phases, it's going to be negative. And that's why he has a negative point here. Right? So as he works his way around the circle, so here I am, you can see that, again, the two vectors are nearly equal magnitude. In fact, in this case, the length of the vector to the pole is longer than the length of the vector to the 0. So in fact, this is dipping below 1. You can see it's slightly below 1 because the ratio of those magnitudes is going to be less than 1. Now what about the phase? Well, the phase to the 0, I don't know, is something like 120 degrees. This angle here is still bigger, right? The angle formed by this vector, the vector to the x with the x-axis, is bigger than the angle formed from the O to here with the x-axis. So it's still negative. But the angles are very close. Now if you keep working your way around, it becomes more and more like that. Finally you're going to get to pi, and here again you have both are real, and in this case, again, the vector to the pole is larger than the vector to the 0. So the ratio is going to be less than 1. Okay? And then you can go down in the negative direction and get something similar. Okay, so that can be helpful, but you can simply do the math computations without the picture. But it does give some intuition. Okay, so I want to keep these videos short, so I'm going to stop here, and then we'll pick up with slide 28 in the next video.